Welcome to the lecture series on process integration. This is module 5, lecture number 4, and topic of the lecture is design for threshold problems. We have already seen pinch design methods or the rules through which a heat exchanger network can be designed. Now, we demonstrate the above rules through designs of heat exchanger network. For this purpose, we have selected 3 different problems. One, design for threshold problems, the other design for a single pinch problem, and the third design for multi pinch problems. Now, let us see what is a threshold problem. Characteristics of threshold problems are that these either need hot utility or cold utility, but not both. Thresholds problem can be divided into 2 broad categories for the purpose of design. The first type, the closest temperature approach between the hot and cold composites is at the non-utility end, and the curves diverge away from this point. Now, this shows 2 examples of such problems. In the first problem, this is the non-utility end. Here the hot utility requirement is 0, and in the other end, which is a utility end, here there is a requirement of cold utility. Now, the delta T is minimum here, but while we go away from this, the delta T increases. Similarly, for this problem, at the cold end the utility is 0. So, this is called non-utility end, and here there is a requirement for hot utility, because this cold stream is to be heated from this point to this point. Now, the delta T minimum is at non-utility end, which is the cold utility end here, and as we go away from it, the delta T is increasing. So, this is one set of problem, and it is a simple one, because delta T is less here and then it is increasing continuously in this also. Now, the second type of problem is there is an intermediate near pinch which can be identified from the composite curves as a region of close temperature approach. This is the pinch area where there is no flow of heat, and this is non-utility end, and then when we go from non-utility end, we find a area here which is a near pinch area or a pseudo pinch area, and then the delta T increases, and this is a area where cold utility is required. So, here is a non-utility end, here we do not need hot utility, and the hot utility requirement is 0, but this is not the minimum temperature. Here the minimum temperature is not there. When we approach, here we find a second point where there is a near pinch area or a pseudo pinch area. Similarly, here this is the non-utility end where the cold utility requirement is 0, but here there is a hot utility requirement. So, when we go away from here, we find a zone here where the delta T is very less, and this will be called a near pinch or a pseudo pinch area. So, we have seen that 2 type of problems can arise out of threshold problems, and we will take the example of both problems and we will design heat exchanger network for the above two problems. As per the PDM rules, the design should start where the problem is most constricted. This we have learnt. Now, if the design problem has a pinch, then the problem is most constricted at the pinch and thus it should start from the pinch point moving away from it. If the pinch or the most restricted part otherwise is at the non-utility end, then the design should start from there and we should move away from the pinch. Or if the most restricted part is near pinch or pseudo pinch, then it should start from there moving away from it. But in this one thing we should remember that in a threshold problem at the near pinch there is a flow of heat. So, we should not confuse with this. In ordinary pinch problems at the pinch the heat flow is 0 and hence the problem is divided into two parts, whereas in a threshold problem it is not there. In the near pinch area there is a flow of heat. This will be clear when we take up the examples. So, we take this problem where there are two hot streams and two cold streams. Their Cp supply temperature and target temperatures are given and delta T minimum is taken to be 5 degree centigrade. Now, if we plot the stream data here, this vertical line shows process pinch. We saw all the streams are in one side and here there is no stream. Now, this shows the composite curve of the problem. Here this is hot composite curve, this is cold composite curve and this is the pinch process pinch area and this is the pseudo pinch. So, why process pinch here? Because no heat flows here, hot utility requirement is 0. So, is a process pinch area, this is a pseudo pinch area and the design will start from here pseudo pinch and it will move in this direction as well as in this direction. So, I expect that for this problem we have to design the whole problem in two parts. Now, this part which is below the pinch, but above the pseudo pinch and that is why it will be called a hot end and this is below pseudo pinch. So, this will be called a cold end. So, the rules and regulation of pinch design for hot end will be applicable to this area and cold end will be applicable to this area. We see that here the problem is most constrained, that is delta T minimum is very less and then the delta T increases in this direction and delta T also increases in this direction and there is a cold utility requirement here. Now, it is most interesting part is that at this pseudo pinch some amount of heat which is we will calculate and see, it comes out to be 17.5 kilowatt is passing from hot end to cold end. which is a uncommon in a process pinch area or in a utility pinch area, but we have to remember that in a pseudo pinch the heat transfer takes place from hot to cold. If we see the same problem in a Gantt composite curve, this is the amount of heat which is passing through pseudo pinch, and this heat which is coming from here, if I consider a vertical heat transfer from this hot streams, is directly passing to the cold stream here below, and it is not doing any work, it is directly passing to the cold stream, and thus it is a total loss of heat. Here the cold utility requirement is 55 kilowatt, given by this distance, and this distance shows that how much heat is passing through the pseudo pinch area. So, these are the requirements for hot utility requirement is 0, cold utility requirement is 55 kilowatt, pseudo pinch is at hot pinch will be the hot pseudo pinch is 85 degree centigrade and the cold pseudo pinch is 80 degree centigrade, difference is 5 degree, and heat flows through this pseudo pinch is 17.5 kilowatt, this we will calculate. Thus, in this case it is advisable to treat the problem as a pinch problem and pseudo pinch as pinch. This is important. We are considering pseudo pinch as pinch, but it does not qualify the pinch completely, that is why we call it pseudo pinch, because heat will be transferred through this pseudo pinch and the amount is 17.5 kilowatt for this problem, and design should be away from the pseudo pinch in both direction. Difficulty in treating this problem is as pinch problem is that one half of the problem, the hot end, will not offer any flexibility to match against the hot utility stream, because the hot utility stream requirement in this half is equal to 0. Now, the enthalpy available with the hot streams up to the pseudo pinch is 367.5. This is the hot stream number 1, this is hot stream number 2. So, this is 367.5 kilowatt. Similar, the heat required up to the pseudo pinch by the cold streams, this is the first stream, this is the second cold stream, this comes out to be 350 kilowatt. So, if I compare these two or deduct from hot to the cold, it comes out to be 17.5 kilowatt. So, 17.5 kilowatt of heat will pass from this hot stream to the cold stream. So, this is the red area which shows heat passing from here directly to the cold stream, and this amount is 17.5 kilowatt. This amount of will pass from cold section to the hot section to the cold section without doing any fruitful work. So, I am not getting any work out of this heat flow, thus offers an opportunity to use it in this design. Now, this is the grid diagram and this is the pseudo pinch area. So, my design is below the pinch and above the pseudo pinch. So, this zone is below the pinch, process pinch, and above the pseudo pinch area. So, we call it a hot end, and here it is written below pinch, this is below process pinch, and we call it a hot end. So, the hot end rules and regulations are here. That means, NH should be less than or equal to NC. This rule is satisfied as NH is equal to NC here. Now, the other rule is CPA should be less than or equal to CPC. So, while putting match, we will see this rule is taken care of. So, here we have 2 hot streams with 3 and 1.5, 3 and 1.5, and there are 2 cold streams 2 and 4. So, these are hot streams and these are cold streams. Now, let us put the match. Now, here this stream has 267.5 kilowatts with it, and this requires 240 kilowatts. So, based on this CP rule, if I put this match 3 to 4, this is perfectly agreeing with this rule, CPC 4 is more than CPH 3. So, I can put this match, and as per the Teachoff rule, I can pass 240 kilowatt of heat energy from this stream to this stream. So, the heat exchanger number 1 match is correct match or acceptable match, because it obeys all the rules, and this is a pinch match. So, the rules has to be obeyed very strictly for this case. So, once I put this match, this stream is ticked off. Now, I put the second match, which is between 1.5 and 2. Here also the rules are followed. CPC, which is 2, is more than 1.5, which is CPH. Now, we see that this amount delta H with this stream is 82.5. So, we can pass on the whole amount to this stream, because it can take 110 kilowatts, which is more than 82.5 kilowatt. So, this match is as per the CP rules, and this is also a pinch heat exchanger, and that is why this rule has to be obeyed very strictly. So, this stream is ticked off now. Now, I put a third match between 3 and 2. This match is not obeying CP rule, because CPH is more than CPC, and this match is for 27.5 kilowatt, and once I put this stream is tick off, because from here 82.5 kilowatt has come here, it was needing another 110 kilowatt, 110 minus 82.5. This comes out to be 27.5 kilowatt. So, I have put a 27.5 kilowatt heating here from here. So, this stream is ticked up. So, this is ticked up, this is ticked up, and this is ticked up. Now, this should cool down up to 85 degree centigrade, but and if it cools down up to 85 degree centigrade, it will contain 285 kilowatt, but as this stream will take some heat which is equal to 17.5 kilowatt to the other side, this cold end, this cannot cool down to 85 degree centigrade. So, it cools down to 90.83 degree centigrade, which is a summation of this and this. So, if I add 240 to 27.5, 240 with 27.5, this comes out to be 267.5. So, it will pass only 267.5 kilowatt to these cold streams, and remaining 17.5 kilowatt will be passed to the cold end, and hence it will not cool down to 85 degree centigrade here, it will cool down to 19.83 degree centigrade. So, this has to be observed that this is more than the pseudo pinch temperature of 85 degree centigrade. So, 17.5 kilowatt will pass from this hot end to cold end. Now, the only stream which has residual heat was 17.5 kilowatt left is stream 1. The stream 1 will not reach the pseudo point of 85 degree centigrade, instead it will reach up to 90.83 degree centigrade. So, that heat equal to 17.5 kilowatt is passed to cold end of the problem through pseudo pinch. Please note that to keep the below pinch hot end under thermal balance, stream 1 will only cool down to 90.83 degree centigrade and hence can be considered to be ticked off. So, in the last slide we have seen that all the streams have been ticked up. So, our design of the hot end of this problem is complete. Now, we have to design for the cold end. So, the hot end is complete and this is the pseudo pinch, 17.5 kilowatt is passing to the cold end. So, we have to design this cold end. So, I have a table here, CP table. So, this is below pinch design, but this is cold end, that means it is below the pseudo pinch also, and the rules are this, which are the inverse or the reverse of the rule of the hot end design. Now, this 7.5 kilowatt which is passed here has to pass to the cold fluids, but here I have only one cold and two hot, and then I have to use a cold utility. So, first we put a match between the CP 3 and CP 2.0, this match, and here CPH is greater than CPC. So, this rule is valid, this rule is valid. Here there are two hot streams and one cold streams, and hence this rule is also valid. So, once I place this, this stream is ticked off, this stream is ticked off. Why? Because now this stream has got a delta H of 92.5 kilowatt, including this 17.5 kilowatt. So, this is 92.5 kilowatt. So, this is ticked off, and this you can calculate. So, this comes down from 90.83 minus 60 into 3, which is almost equal to 92.5 kilowatt. So, this stream is ticked off. Now, I put a second heat exchanger between this 2.0 and 1.5. So, this is 2.0 and 1.5. This match does not obey this CP rule. This match does not obey the CP rule, whereas this match obeyed the CP rule. This is a pinch heat exchanger. So, it has to obey this CP rule very strictly, but this is a non-pinch heat exchanger. So, CP rules can be somewhat diluted for this, unless otherwise we cannot put a match, but we have to see that this does not violate the delta T minimum criteria. So, here delta T is 66.67 and this is 20. So, this is not violating. So, this is this stream is ticked up, and then we are putting a cooler here which is 55.55 kilowatt, which was the required cold utility demand. Here also we can see that this temperature is 33.75 and this temperature is 85. So, here the delta T minimum criteria is not violated, here the delta T minimum criteria is not violated. So, this match, which is 2 and 1.5 match, which is a heat exchanger number 5, is all right. And being a non-pinch heat exchanger, it did not violated the delta T minimum criteria, otherwise it would have violated if it would have been the pinch heat exchanger. Now, from this 66.67 degree centigrade to 30 degree centigrade, this has to be cooled down by a cold water, which is a cold utility, and it will be 55.0 kilowatt, which was the requirement of our cold utility. And all the streams are now ticked up, and hence this design, cold end design, is now complete. So, the hot utility requirement for the design is 0 kilowatt, the cold utility requirement is 55 kilowatt. This is what we have can observe from the PTA, and hence the design has matched with the targeted values. So, this is the complete design of the heat exchanger network for the problem where there is a pseudo pinch. Now, we have seen one part, that is, if the problem has got a pseudo pinch, how to handle it. Now, we see a second problem where the problem does not have a pseudo pinch. The delta T minimum is at one end, which is non utility end, and then it increases. So, if such a problem is there, then how to handle it? So, this is our problem where there are two hot streams and two cold streams. Delta T minimum is 10 degree centigrade, and the composite curve for this is this. That means, this is the non utility end where hot utility requirement is 0, but there are some cold utility requirement here. So, hot utility requirement is 0, cold utility requirement is 239.5 kilowatt. So, the design will start from here and it will move in this direction, because here the delta T is opening up, and this is the minimum delta T available. When we go move from in this direction, the delta T is increasing. This is the GCC of the threshold problem. We see here there is no hot utility requirement, it touches this y axis, but there is a cold utility requirement here 239.5 degree centigrades. So, how to design a heat exchanger network for this problem? Now, this is the stream data. Here at the hot end there is nothing, no streams. At the cold end all streams fall. So, in a threshold problem we always face such type of problems. It is almost half of the ordinary pinch problems. So, here we will be designing below pinch, below process pinch area, and that is why it will be a cold end. And if it is cold end, then in my CP table the rules will be for cold end design. Here we see that NH and NCs both are here, there are 2 and 2 streams, but it is not solving our purpose, that is why we will have to split a stream. So, if I split a hot stream, then I have to also split a cold stream to make the number equal, and this splitting is done because it will not have that Cp, it will not conform to the Cp H rule sum matches, and that is why you have to go for this. So, we are splitting a hot streams and we are splitting a cold stream. So, the first match we are putting between 3.004 and 2.5. So, this rule is valid for this 3.004 and 2.5. Cph is more than Cpc. This stream has got 200 kilowatt of energy it can take, and this part that is having 3.004 Cp can give you 200 kilowatts. This we can calculate 190 Now, the second heat exchanger which we will be putting is with this and this, that means 1.8 to 1.725. This is 1.8 Cp of this stream and this is 1.725. So, as for this rule, this is perfectly okay, and we can put a match of 207 kilowatt and we can tick off this stream. Then we can put a third match between 0.495 and 0.278. This is also according to this Cp rule. So, this match is 33 kilowatt and this along with this cooler 239.5 kilowatt ticks up this. Now, we can calculate the temperatures. This is 140 degree centigrade, cool downs to 20 degree centigrade when I pass 33 kilowatt of energy, and this from 140 degree centigrade to 20 degree centigrade it cools off when it passes 207 kilowatt of energy. This you can calculate 140 minus 20 into 1.725 comes out to be 207. So, 140 minus 20 into the Cp of this stream which is 1.725 comes out to be 207, and that is why this is ticked off. Similarly, this is 190 So, if you do this 190 minus 123.43 into 3.004, this will be around 200 kilowatt. So, this part of the stream is ticked up. Similarly, 190 minus 123.43 equal to this into 0.495 comes out to be about 33 here. So, this part of the energy with this part of the hot stream is about 33 kilowatt, it passes to here, and this part has got 200 kilowatt, it passed to here. So, this requires 200 kilowatt, this is ticked off, and the heat which has with this stream is 200. So, this 207 plus 33. So, it comes out to be 240 kilowatt. So, 240 kilowatt heat is passed to this two streams, and that is why it is ticked off. So, this is ticked up, this is ticked up, and this is ticked up. So, here it is 123.43 degree centigrade, this has to be cooled down to 55 degree centigrade. So, it requires a cooler. So, we placed a cooler which has got a capacity of 239.5 kilowatt. Now, all this with this is ticked up. So, all the streams are ticked up, and hence this, and the cold utility requirement was 239.5 kilowatt, and this cooler is taking 239.5 kilowatt. So, it is, this design is complete and according to the targeted value of 239.5 kilowatt of cold utility. So, this completes this design. Thank you.